All right, my 130s. So I'm going to see if this video actually works. I don't know what the issue is at this point. I'll make this video for the next bit. I went through numbers 1 through 10 just to keep you guys posted. What I'm going over right now is homework alternate assignment, chapter 6. And for 29, with the LAC group, I went over number 1 through 10. I'm going to see if I can get that recording up for you. And then today, I'll start with number 11 and just see how far I can go. All right, let me clear this and then go ahead and, okay, hopefully you can see that. So I'm gonna start with number 11. I gotta rearrange some things here. Let's see, I don't think this is gonna work for me. So still trying to get used to doing all this on my home computer instead of my work one, which is not ideal in various ways, but it's a part of the process. All right, so just as a little refresher in case this doesn't work out, chapter 6 covers roots and radicals. Oh, Lord have mercy. Okay, hold on. Let me pause and see if I can figure this out. All right, everybody. So I got all the spacing and stuff worked out, and I just went ahead and wrote in what I want to review first before playing around with this too much more. So basically what I talked about yesterday was that roots and radicals are the same thing. And essentially, you're probably already familiar with like a square root or a cube root. Here's how they look. Whatever's underneath the radical sign is called your radicand. And whatever you have above the radical sign, like kind of in this little house nook, is called the index. The only one that you won't see if you have the square root of A that means that your index in is actually equal to 2. We don't write that there though. Okay. So quick example, if I have the square root of 64, essentially what that index tells me is how many factors that need to be the same I need to look for under my radical sign. So I know that 64 is 8 times 8. Okay, I have a pair of 8s. So the square root here undoes the square. This is actually 8 squared, square rooted. So that becomes 8. Okay. Now, next, roots and radicals are actually fractional exponents. So if you have the nth root of a, that's the same as a to the 1 over n. So square root is the same as a to the 1/2. Cube root of a, same as a to the 1/3, so on and so forth. So little extra example here. We have a square root 64 again. We know that that would be 64 to the 1 over n power. And n in this case is 2. Inside the brackets here, change, or the parentheses, change 64 to 8 squared. That whole quantity is taken to the 1/2 power. And then remember your exponential rules from chapter 4. This is 8 to the power of 2 times 1/2. Okay, 2 times 1/2 is just 1, so we get 8 out still. So right here, this is simplifying a radical in root form. And down here, simplifying a radical in exponent form. Okay, let me save that, clear this out in a moment as soon as I can. Come on. One of my boxes has disappeared, the one where I can start and stop recordings and such. So give me a second with this. Come back, come back. There we go. Okay, let me clear all this out. All right, so question 11, simplify each radical expression as much as possible. Assume that the variables represent any real numbers. For this part, essentially you can kind of think of this 2 ways. Let's look at part A first. You have the 4th root of 1 minus 5x to the 4th. That would be 1 minus 5x to the 4th to the 1/4. So that's going to give you 1 minus 5x because of this part. But there's something that you have to remember with even roots. You're going to need to put an absolute value around this, because even if you have a number in here for x that makes 1 minus 5x negative, when you take it to the 4th power, it turns positive. Okay. Okay, hold on a second. Okay, so for part A, you're going to have the absolute value of 1 minus 5x. Specifically, even roots, meaning that n is equal to an even number. Whatever you have inside the radicand, that part, when you take the root, is going to need to be absolute valued. Okay. With an odd root, you will get whatever you come out with. And the reason is because even roots or odd roots can be either positive or negative when they come out. So let me just go ahead and go through part B first. we have a cube root w to the fourth, sorry, cube root w to the third. That's going to be w to the third to the 1/3 power. And that comes out to be w. If w is negative, you'll get a negative cube root. If w is positive, you get a positive cube root. Okay. Over here, one more time, if you have 1 minus 5x, and that turns negative, when you take the fourth power of it, it's going to be positive. So the fourth root is always going to be a positive number, hence why we have the absolute value. Let me save that. And then one more way that you can think about both of these problems. Let me go ahead and erase. All right, I have my fourth root. 1 minus 5x, the quantity to the fourth, that's essentially writing your 1 minus 5x 4 times multiplied together. Okay, you have 4 of these factors. So when you take the fourth root, only one of the factors comes outside of the absolute value. And then because your root is even, you're going to go ahead and put absolute value around. Okay, last bit. You have cube root w cubed. That's going to be the same as writing the cube root of w multiplied 3 times. You have 3 factors here. So for every 3 factors you get, you just take one of those factors out of the radical. And because it's an odd this time, no absolute value needed. Okay. All right, that covers number 11. Let me go ahead and clear all this out. Let's go over number 12 and 13. We're looking for the domain of our functions. So essentially, remember we had 2 domain rules in the past. So any function, actually, and let me put every function has domain negative infinity to infinity unless one of the 2 rules apply or these rules apply together. One is that your denominator cannot be equal to 0. Okay, so the values that make your denominator equal to 0 will not be in your domain. This was chapter 5 mostly, when you had rational equations and expressions. So a quick example of that, if I have the function f of x is equal to 1 over x plus 2, I'm looking for values that make x plus 2 equal to 0. So x would equal -2. If I have that, my function evaluated at -2 would give me 1/0, which is undefined. Okay, so if I were looking for interval notation for the domain, or we can make a number line for this. These are my x values. -2 is the only one that gives me a 0 in the denominator. Everything else is okay. So -infinity to -2, not including both. Union -2 to infinity, not including both. Okay, so that's the first rule. And then the second rule is mostly for chapter 6, from what we learned so far. But we have seen it before. So if you have a root, and n is even. Okay, specifically, you have a root with even index. Then from there, your radicand A must be greater than or equal to 0. And those are the values that are allowed in your domain. So example, if I have f of x equals square root x plus 2, okay, and I'm looking for the domain, I'm looking for where x plus 2 is greater than or equal to 0. That applies for x values greater than or equal to -2. So graphing that, okay, x values greater than or equal to -2. So my domain and interval notation, these are the values that I can use because they make the radicand 0 or positive. I'll look into that in a second, but we put -2 up to infinity. Okay. Now, last thing I want to say about that is the reason why this occurs. Let's look at x versus f of x. We're going to put -3, -2, and -1 and 0. So if I were to plug in -3 here, I get the square root of -1, which is not a real number. Okay, so that's why it's outside the domain. Of f. If you plug in the other values, -2 plus 2 is 0, square root of 0 is 0. -1 plus 2, that's 1. So that'd be square root 1, which is 1. Plug in 0, it's square root 2, which is irrational, but still a real number. Okay. Let me save that and let's go into numbers 12 and 13. Okay, so for number 12, find the domain of this particular function. So we have an even root. which means we will not have negative infinity to infinity for our bounds. We do need to check when our radicand sorry, I want to do that in green. Check when your radicand is greater than or equal to 0. Okay, so subtract 7 both sides. Divide by a -7. And don't forget to flip your sign. So it's saying that my x value should be less than or equal to 1 in order for my radicand to be positive, thus giving me a real valued number for v. So go ahead and draw your number line. Here's 1. You can include it in everything less than that. Okay, so interval notation for this would be negative infinity to +1, parenthesis bracket, accordingly. Okay, let me go ahead and clear this out. So for number 13, notice you have one even root and one odd root. Okay, so for f of x equals the 4th root of x plus 3, we have an even root. So we must check when the radicand is greater than or equal to 0. So for this one, subtract 3 both sides. So your number line, you have -3 included and everything greater than that. So for this first one, you have -3 to infinity. Now with g of x equals cube root 4x minus 8. Remember, it doesn't matter if the radicand is positive or negative or 0, you will still get a real valued number out. Okay, so cube root of negative numbers would be negative. Cube root of positive numbers will be positive, and cube root of 0 will be 0. So you do not have a denominator to worry about. You don't have an even root. That automatically means you have negative infinity to infinity for your there we go, for your interval domain. Okay, I don't know what is going on with this. There we go. All right. Let me save this and continue. All right, let's see if I can smoothly do this. As a matter of fact, what I'll do, I'm just going to pause the recording while I move to the next page. All right, guys, so this next page, I'm actually going to skip number 14 for now. I would definitely suggest that you look that over in ALEKS. One thing I can mention about it is you want to pick values that make your root nice. So like for this particular example quickly, if I pick x equals 0, I know square root of 0 is 0. That's a nice number. If I pick x to be 1, that's also a nice root. If I pick x to be 2, I get an irrational number. So I would have to approximate this, not such a nice number, okay? For x equals 3, same thing, it's irrational. And then x equals 4, you get square root 4, which is 2. So that would also give me something nice. So these are the x values I want to include in my table. And then I find the corresponding f of x values by plugging in. Okay. So let me know if you have troubles with those particular problems, and I can cover some of those. Let me clear this out. And then move on down. Number 15 is next. Write the following as an exponential expression. So this actually goes into what we were talking about with root radical form. Which you see here. And when you're writing it as an exponential expression, that means change your radical to an exponent, fractional exponent. So here, our root form, we have the radicand u to the 5th. That becomes the base for our exponential form. Radicand becomes the base. And then this index you have here becomes a fractional exponent. So index becomes fractional exponent. So remember, you're going to have 1 divided by, and then you have your n value there. Okay, now don't leave it like this because you can still multiply the exponents to make it nicer. So your final solution for number 15 should be u to the 5/6. Let me save that and keep going. Question 16. We're asked to evaluate particular expressions. So the first one I have is 81 to the 1/4. You do not need to change this back into a root. Use your exponential knowledge. Try to write 81, preferably as a 4th power if you can. So 81 is actually 3 to the 4th. And that's taken to the 1/4 power. So we have 3 to the 4th to the 1/4. Remember, multiply these exponents, you'll get 1 here. So you get 3 out. Okay. And then looking at 27 to the 1/3. Similarly, try to write 27 if you can with a 3rd power. So that would be 3 to the 3rd. You have your power of 3 times 1/3, that gives you 1. So you still wind up with 3 in this problem as well. All right, let me pause for a moment. All right, so let me keep going here. Number 17 is next. The first one we have is 81 to the -3/4 power. First thing I would suggest, like, don't worry about trying to make this into a positive exponent or whatever, since you have numbers there. First thing you want to do, change that 81. Oops, change it completely. You want to try, ideally, when you have an exponent on whatever base you get, you want to try to cancel the numerator of the inside exponent with the denominator of the outside exponent. So that doesn't make sense yet. I know that 81 is 3 to the 4th power. And I'm taking that to the negative 3/4 power. So that's going to be 3 to the 4th times negative 3/4. So this is what I meant. See how the exponent of the inside will cancel out with the exponent out here on the bottom? So numerator exponent inside cancels with denominator exponent outside right here. So you're left with 3 to the negative 3rd power. Remember that that is 3/1 to the negative 3rd power, which becomes 1/3 to the 3rd power. We get 1/27. Okay. For the second part here, we have 1/32 taken to the negative 2/5 power. For this one, you can think about it like this. This is 1/2 to the 5th. Because 1, and as a matter of fact, I can even do a little extra here. So 1 to any power is going to be itself 1. So 1 is the same as 1 to the 5th. And 32 is the same as 2 to the 5th. You have a negative 2/5 power out here. Now, essentially, inside the parentheses, that would be 1/2 to the 5th power. And you have negative 2/5 out here. So that's 1/2 to the 5th power times negative 2/5. So 5 cancels with 5. You have 1/2 to the negative 2, which becomes 2/1 squared. And that is going to be 4. Okay. Let's keep it moving. Let me pause the recording while I flip page. All right, so number 18 is going to be next. For this part, it might help to remember some previous exponential rules to clean up the work a little bit. Okay, let's say we were trying to simplify this. Okay. Y to the A times Y to the B, all divided by Y to the C. Well, what would we do with our exponents in each case? So let's just look at the numerator first. We could combine the y's. That's AY's multiplied together times BY's multiplied together. So total, that'd be A plus B. for your new exponent. And you still have y to the c on the bottom. And then in the next step, remember that essentially when your y's combine with a quotient like this, you're going to subtract the bottom exponent from the top. So we have a plus b, the exponent minus c. So we should have y to the a plus b minus c. Note in this case, a is 1/4, sorry, negative 1/4. B is 3/2, and C is 1/3. Now you don't have to actually do it with an ABC. You could just do this straight out like, okay, I know I need to add these exponents and then need to subtract this exponent. That's fine too. But it just kind of makes it a little easier for me to see personally. So I'm going to do A plus B minus C over here. That's negative 1/4 plus 3/2 minus 1/3. You can go ahead and find the LCD for the entire thing if you want, or just do 2 terms at a time. I'm going to find the LCD for the whole thing. Between 2, 3, and 4, the LCD will be 12. So I have negative 1/4. That's going to be multiplied by 3/3. I have 3/2. That'll be multiplied by 6/6. And I have negative 1/3. That's going to be multiplied by 4/4. Okay, so I have negative 3/12 plus 18/12 minus 4/12. That's negative 3 plus 18 minus 4 all divided by 12. So let's see, what's that give me? 15 minus 4, 11/12. Okay. So what I wind up getting, remember that's my exponent right here. And I still have y as my base. Okay. Question 19 is next. We want to simplify this expression. So I'm going to start this one up a little bit higher. Okay, so note that z and y are different variables, so their exponents can't be combined. But remember your rules from exponents. You have a z to the 5/2. That can be taken to the negative 1/3. And then that's going to be multiplied by y to the 1/5, taken to the negative 1/3 power. Okay, so you can split these. What I would suggest from here, you're not going to write your answers with negative exponents, but you can go ahead and multiply your exponents out first. We have z times, z to the 5/2 times negative 3. And then we have that multiplied by y to the 1/5 times negative 3. Remember that's over 1 for the 3's. So we have z to the negative 15/2. And we have a y to the negative 3/5. Now, if it confuses you to do this together, like you could just go ahead and put this all under one and change these to positives. But if you're unsure, just do them separately. Remember, 1 here, and then z to the 15 halves. And then 1 over y to the 3/5. So that's 1 over z to the 15 halves, y to the 3/5. Save that and continue a little bit more for today. I actually did Pythagorean theorem one in the last video, so I'm going to wait on this one for now. If you have questions, ask. I think that number 21 is going to be a good one to end on right now. So you have square root 180, and 180 is not a perfect square. Okay, when you're simplifying a radical, essentially you just don't want to leave any perfect indices under here. So like this is a square root. Don't leave perfect squares in the radicand, okay, as factors. So what we're going to need to do is prime factor 180. So 180 is 18 times 10. 18 is 6 times 3. 6 is 2 times 3. Prime, prime, prime. And then over here for 10, we have 2 times 5. Okay, so 180 is actually 2 times 2 times 3 times 3 times 5. And remember, that's still square rooted from our original expression. You have a pair, you have a pair, right? So if it helps you, write this as exponential form under here. That's 2 squared times 3 squared times 5. So from here, you have a pair of 2's. So 1, 2 comes out of the radical. You're going to multiply that by, you have a pair of 3's, 1, 3 comes out the radical. And then this part over here, you can't do anything with it because there's not a pair. So you're actually going to leave it underneath the square root. Okay, and then multiply the front. You get your final answer, 6 root 5. So next week, I would like to practice problems like this one in terms of simplifying radicals. That's what a lot of this next bit from chapter 6 is going to be. Essentially like an example of what's going to happen next week. We have square root 180. How does that compare to cube root 180? And compare to fourth root 180, and so on and so forth. But I'm going to give you a better example, one that has more primes that you can factor out, and then also has some variables in it. So do stop by the room next week. I'll give you guys some updates over the weekend in terms of how the cloud recordings are coming and how the structure will be for next week. Let me know if you have any questions, concerns in the meantime, and I will see you guys next week.